Okay, so the next major topic that we're going to discuss to start to begin to draw accurate depictions of organic structures and orbital pictures is this idea of valence electrons and bonding. So atoms typically lose or share their most readily accessible electrons and their highest energy electrons. So the most readily accessible highest energy electrons are the valence electrons, which are also defined as electrons in the highest energy principal energy level, the largest N. Now, in addition to this idea that atoms will use their valence electrons to engage in bonding, we'll also discuss what's a rule that's known as the octet rule, which is this idea that atoms generally gain, lose, or share electrons to reach a noble gas-like configuration, which is 8 valence electrons. Now, one way that we can very easily identify the valence and core electrons is using what are known as abbreviated electron configurations. So as review from Chem 101 and Chem 102, your general chemistry sequence, in our abbreviated electron configurations, looking, for example, at fluorine. So fluorine's configuration is 1s2, 2s2, 2p5, okay? So rather than writing out our core electrons, instead, we're going to look at our core electrons and equate that core electron, that set of core electrons, to the closest preceding noble gas. In this case, the closest preceding noble gas is helium. So in turn, our abbreviated configuration for fluorine would be helium 2s2 2p5. We can clearly label the two types of electrons found in fluorine. For the first type, we have our core electrons. These are electrons that are relatively close to the nucleus and aren't as accessible for chemical bonding in most cases. The outermost electrons, the electrons with the largest N value, are known as the valence electrons. Now, an interesting thing for counting valence electrons is fluorine is a 7A element, and as we can see very clearly, fluorine has 7 valence electrons. In general, most main group elements have valence electrons equal to their group number. So I'd like you to take a moment and I'd like you to write out an abbreviated electron configuration for oxygen and neon, and don't be shy to share your results in the chat or unmute and share your proposed responses verbally. And we'll discuss these two electron configurations in about 2 to 3 minutes. Let's try to get some responses in the chat or using the annotate feature or verbally.
For oxygen, wouldn't it be the same thing? It'd be helium 2s2 2p4?
Yep, exactly right. So for oxygen, the abbreviated configuration would be helium 2s2 2p4. One thing to note, oxygen is a 6A element, so it has 6 valence electrons. Likewise, I already see someone proposing a response for neon. Yep, that's exactly right. Allow me to clear annotation just so that way all the annotations will save in one document, but that proposed response was exactly correct. So for neon, our abbreviated configuration is helium 2s2 2p6. Neon, being an 8A element, has 8 valence electrons, or a full valence shell. Okay, perfect. So we've reviewed this idea of counting and identifying valence electrons. Now, if we look at general trends in the periodic table, we notice that main group elements have valence electrons equal to their group number. So in each group, in each column of the periodic table, elements in each group have the same number of valence electrons. Now, what we can do with this information is that we can start to draw what are known as Lewis dot structures. And in Lewis dot structures, we abbreviate our valence electrons using dots to represent electrons. So one dot is one valence electron. So for example, lithium is a 1A element. We have one valence electron, one dot. Beryllium, 2A, 2 electrons, 2 dots. Boron, 3A, 3 electrons, 3 dots. Carbon, 4 electrons. Nitrogen, 5 electrons. Oxygen, 6 electrons. Fluorine, 7 electrons. Neon, 8 valence electrons. Note, this set of Lewis dot pictures that I provided you is comprehensive for all of the main group elements, because elements in the same group, elements with the same group number, will have the same number of valence electrons. So for example, if I'm looking at sulfur, how many valence electrons does sulfur have to its name? How many valence electrons does sulfur have?
6.
6, yep, exactly. 1, 2, 3, 4, 5, 6. Because sulfur is a 6A element. Likewise, for chlorine, chlorine is a 7A element, and it in turn has 7 electrons, 7 dots for its Lewis dot depiction. Wonderful. Okay. So, organic chemistry primarily concerns covalent or molecular compounds, and in covalent bonding, we have a sharing of electrons between atoms. Atoms generally share electrons to form an octet, 8 valence electrons, where our bonding electrons are shared in pairs between atoms participating in a covalent bond, and as a result, these bonding electrons are counted as belonging to both atoms in a bond. So for example, if we look at a chlorine-chlorine bond, let me draw out our bonding electrons. So we have 2 bonding electrons. And in terms of electron counting, we count our bonding electrons as belonging to both of our atoms, while lone pair electrons or non-bonding electrons are electrons that are not shared between atoms. These lone pair electrons are counted as belonging only to the atom containing the lone pair. So if we draw a map to indicate what electrons belong to which atom, we see that the chlorine on the left has 2, 4, 6 lone pair electrons that are belonging exclusively to that chlorine, and it's sharing 2 bonding electrons. So 6 plus 2 gives us 8 electrons surrounding our chlorine on the left. Likewise, for our chlorine on the right, has 6 electrons that it exclusively owns as 6 lone pair electrons, and 2 bonding electrons. So we have 6 plus 2, that gives us 8 electrons total. As we can see, for both of our chlorine atoms, we are satisfying the octet rule. We can also represent these bonding electrons as a line. So this line represents 2 bonding electrons. That's far more common in organic chemistry for bonds to be represented as lines rather than as dots. Does this look familiar to everyone so far? This is the fundamentals of Lewis structures.
Yeah.
Okay, perfect. So let's look at water, for example. The Lewis structure for water looks something like this. The lone pairs are drawn exclusively as a set of dots. The lines are only used to represent bonds. So looking at our depiction of water, I'm going to draw this line Lewis structure out in the form of dots to help us more easily count electrons. So first, let's look at hydrogen. So hydrogen has 0 lone pairs and is sharing 2 electrons. So hydrogen has 2 electrons total. One thing that's interesting about hydrogen is that it prefers to have 2 valence electrons to match the noble gas of helium. So hydrogen, rather than following the octet rule, follows, I guess, what you can call the duet rule, where it prefers 2 valence electrons. Oxygen, if we look at oxygen in this example, it has 4 lone pair electrons and it has 4 bonding electrons, and that in turn gives us 8 electrons total. So as we can see, the octet rule is fulfilled for atoms in this structure, and hydrogen has a noble gas-like configuration in this structure. Okay, so let's talk a little bit about how bonds are represented. So bonds are commonly written as lines between each atom. One line represents 1 bond, which represents 2 shared electrons. We can have a single bond, which, for example, involves sharing 1 pair of bonding electrons. So, for example, these 2 fluorine atoms have decided to share 2 electrons. And as we can see very clearly in each of these examples, each fluorine has 8 surrounding electrons to its name. So the octet rule is favorable because noble gas-like configurations are relatively stable compared to non-noble gas configurations. A full shell is energetically favorable compared to a partially filled valence shell. But the octet rule is more of a soft rule. There are cases in which the octet rule is not obeyed, considering cases such as formal charges. And we'll talk more about those examples later on in the class. Now, just like we can have, for example, multiple lone pairs, we can just as easily share more than 1 pair of electrons between our atoms. So 2 pairs of bonding electrons leads to what is known as a double bond. So for example, in oxygen, you can suppose and draw a Lewis structure that contains a double bond between our 2 oxygen atoms. In this case, we have a total of 4 electrons shared between our oxygen atoms. So for example, we draw 2 pairs of dots between our oxygen atoms. And as a result, if we count the total number of electrons belonging to each oxygen atom, we see each oxygen atom still has 8 electrons to its name. Does this make sense to everyone so far?
Yep.
Perfect. So, when we have 3 pairs of bonding electrons, we call this a triple bond. So this in turn means we're sharing a total of 6 electrons. So nitrogen, for example, has a characteristic triple bond. This in turn means we have 6 electrons shared. This is part of the reason why nitrogen is, well, this triple bond is relatively strong, and that's part of the reason why nitrogen is relatively inert to chemical reactions. If we were to draw out these bonds as explicit dots, we can very clearly see that each nitrogen atom has 8 electrons to its name. As we've touched on previously, hydrogen prefers to have 2 valence electrons to match the noble gas configuration of helium. So we see this, for example, in hydrogen gas, which is H2, where each hydrogen prefers to have 2 electrons surrounding each hydrogen atom. Okay, let's keep going. So Lewis structures are really quite interesting in that Lewis structures allow us to draw plausible, stable structures for a given chemical formula. Now, most stable structures will fulfill the octet rule and minimize formal charges. Okay? So the process that I like to use for drawing Lewis structures is that first you count the total number of valence electrons for all atoms. You essentially make a pool of valence electrons. If the species is a cation, you subtract electrons equal to the charge. If the species is an anion, you add electrons equal to the charge. Next, you determine your central atom. So hydrogen is never your central atom, and the central atom is typically the least electronegative atom. Next, you're going to arrange atoms symmetrically around the central atom or atoms. For n equals 1 and n equals 2 elements, you can only have a maximum of 4 atoms around the central atom. One thing to note, there can be multiple central atoms, especially when we start to look at organic structures, which have multiple carbon atoms, each fulfilling their octet. Now, once you've arranged your skeleton, you're going to form a single bond between the central atom and each surrounding atom. And then you're going to subtract 2 electrons from the total number of electrons for each bond made. Once you've formed a single bond, you're going to place electron pairs, 2 dots, 2 electrons, around the outer atoms, generally prioritizing the most electronegative atoms first. You continue adding electrons until the octet of all atoms is satisfied, or you run out of electrons. If the octet cannot be fulfilled, then and only then will you convert lone pair electrons into a double or triple bond until the octet is fulfilled. I commonly see students jump to drawing double and triple bonds before it's necessary. So that's why I have this explicitly noted in the procedure. Then you're going to check all atoms have a complete octet. Now I mentioned this idea of electronegativity. What is electronegativity? Well, just as a review, electronegativity is a measure of how readily an atom of an element attracts electron density in a chemical bond. Electronegativity increases as you move up the periodic table and to the right on the periodic table. So you can draw an arrow sort of like this for electronegativity. Electronegative elements are primarily nonmetals on the upper right of the periodic table. I've decided to make a nice little hierarchy table to help you rank the electronegativity of common elements that you see in organic chemistry relative to other elements that you'll see in our periodic table. So this is a nice little hierarchy table, and it has some pretty interesting results. And this will be important when we start to look at reagents that have uniquely polarized chemical bonds. One thing I'd like to draw your attention to, carbon and hydrogen have functionally are almost identical in electronegativity. A carbon-hydrogen bond isn't considered polarized for most functional purposes. One other thing I'd like you to note, phosphorus is less electronegative than carbon, and this will come up when we start to look at the unique reactivity properties of phosphorus-carbon bonds, in addition to phosphorus-hydrogen bonds. You may see this in what are known as Wittig reagents, mostly covered in organic 2. Okay, so here's a table of electronegativity. You don't need to memorize the exact values. You just need to be familiar with the relative electronegativity of elements to help understand the nature and polarization of your chemical bonds. So while electrons in a covalent bond are shared, the electrons are not evenly distributed between the two atoms. Depending on the electronegativity, the distribution of electron density may not be even. Okay, so we're going to do some examples now where we have our formula, we count the number of valence electrons, and we draw a Lewis structure. These are relatively simple examples, but I'll start things off by looking at the Lewis structure for chloroform. Oh, sorry, no, this is carbon tetrachloride. So first things first, for our number of valence electrons, for carbon, carbon contributes 4 valence electrons. Chlorine contributes 7 valence electrons, and we have 4 chlorine atoms. So that gives us 32 electrons total. I'm going to draw carbon as my central atom and surround it with my 4 chlorines. Then I'm going to form 1 bond each. So I've formed 4 bonds total, used up 8 electrons. So now I have 24 electrons remaining. So looking at these outermost chlorine atoms, how many electrons do these outermost chlorine atoms need for a complete octet? How many electrons do these outermost chlorine atoms need? They need 6. So we add 2, 4, 6 electrons. And we'll do that for each of our chlorine atoms. So in turn, we've added 6, 12, 18, 24 electrons. We're out of electrons. And as we can see from this structure, the octet rule is fulfilled for each of our atoms. So let's have everyone start working on and drawing out a Lewis structure for ammonia. You can use the annotate tool in Canvas to draw your proposed structure. For those who are having difficulty with the annotate tool, you can also type in the chat the number of bonds and lone pairs attached to nitrogen. So let's spend about another 3 to 4 minutes and let's work on writing out the Lewis structures for ammonia and CH3OH, which is known as methanol. And don't be shy to share your responses in the chat or unmute and share your responses verbally. And don't be shy as well to ask questions related to this chapter. And the response we see for ammonia looks great. Let's try to get a response from a few other people in our course. And I also see some reasonable responses for the ammonia structure in the chat. Let's try to get a few other responses and some responses for the structure of methanol. And we'll discuss these examples in about another 2 minutes. And the responses that I see using the annotate tool look perfect so far. So let's discuss this example, and I'm just going to clear the annotated drawings just so that way I can provide an annotation that saves with the whole document, but the responses I saw in the chat look perfect. So for ammonia, we have nitrogen with 5 electrons to its name. Hydrogen has 1 electron, and we have 3 hydrogens. That gives us 8 electrons total. So nitrogen is going to form a bond with a total of 3 hydrogen atoms, and it will have 1 lone pair remaining. So we go down to 2 electrons after our bonds, and our last 2 electrons fulfill the octet on nitrogen. For methanol, carbon contributes 4 electrons, hydrogen contributes 1 electron, and we have 4 hydrogens, and oxygen contributes 6 electrons. That in turn means we have 14 electrons total. In terms of our central atoms, our least electronegative non-hydrogen atoms are carbon and oxygen. In general, carbon prefers to form bonds rather than have lone pairs. So we're going to place our hydrogens associated with carbon and our last hydrogen associated with oxygen. So the reason why I drew ammonia in this way is to start to respect the inherent molecular geometry found in ammonia. We'll talk more about molecular geometry and VSEPR theory momentarily. Now that we have our skeleton in place, remembering that carbon in general, for formal charge reasons, prefers to form bonds, we're going to form 1 bond each between each of our skeletal atoms. We have 1, 2, 3, 4, 5 bonds, 10 electrons. We have 4 electrons remaining. The atom with the incomplete octet is oxygen, so we're going to place 4 electrons on oxygen. So this is our complete valid structure for methanol that fulfills the octet rule. Does this make sense to everyone? Does this process seem familiar to everyone?
Yep.
Okay, perfect. So let's keep going now, and let's do a few examples where we have to invoke double or triple bonds. Looking at formaldehyde, we have 1 carbon, which contributes 4 electrons. For hydrogen, it contributes 1 electron, and we have 2 hydrogen atoms. And then for oxygen, it contributes 6 electrons. That gives us 12 electrons total. For our central atom, the least electronegative atom is carbon, and we're going to surround it with our remaining 3 atoms. Next, we're going to form 1 bond each. That in turn gives us 6 electrons remaining. And where do we place our remaining 6 electrons? Where do we place our remaining 6 electrons? Oxygen, exactly right. 2, 4, 6. We're out of electrons. However, is the octet rule fulfilled? Is the octet rule fulfilled for all of our atoms? No. So what we're going to do is we're going to convert one of our lone pairs into a bonding pair of electrons. That in turn gives us the final valid Lewis structure that fulfills the octet rule for all of our atoms. Any questions on this example? Let's keep going now, and I'd like you to work and write out a Lewis structure for hydrogen cyanide. And You can either draw the structure using the annotate tool, or you can tell me the number of bonds to carbon in the following structure. And we'll discuss this example in another 2 to 3 minutes. And the responses I see in the chat look great. And for the annotate feature, the response I see using the annotate feature is also perfect. So let's clear these annotations just so that way it all shows up in the same note set. But the responses I see from the class look perfect. So let's now discuss this example. So hydrogen contributes 1 electron, carbon contributes 4 electrons, and nitrogen contributes 5 electrons. We have 10 electrons total. We place carbon as our central atom and surround it with hydrogen and nitrogen. Let me draw it up here so that way I have some space for the later steps. Then we form 1 bond each. That in turn gives us 6 electrons remaining. And our remaining 6 electrons go to fulfill the octet of nitrogen. We now have 0 electrons remaining. However, does carbon have a complete octet? Does carbon have a complete octet? No. So we're going to convert one of our lone pairs into a double bond. Does carbon have a complete octet now? No. So we're going to convert another lone pair to an additional bond. This gives us this final structure that fulfills the octet rule for all of our atoms. Note, the electronegativity rules are really important in identifying the fact that carbon is our central atom rather than nitrogen. Okay. So, for more difficult structures, for more complicated structures, the molecular formula itself provides a hint on the connectivity of atoms in your structure. So, in general, most formulas in organic chemistry will contain information on the connectivity of atoms. So, for example, CH3COCH3, we can begin to see that the way the formula is written provides us a little bit of information in terms of how the atoms are connected together. So counting valence electrons for carbon, we have 4 electrons times 3. For hydrogen, we have 1 electron times 6. And for oxygen, we have 6 electrons. So 12 plus 12, that gives us 24 electrons to work with. So what I'm going to do for my skeleton, of course, I'm going to draw one of my central atoms as carbon. My other 2 central atoms will be my other 2 carbons in my skeleton. The CH3 moiety, or the CH3 functionality, suggests I have a carbon with 3 hydrogens bonded to it. And I'm going to place my oxygen atom attached to my central carbon atom. This CO functionality is actually an indicator of what is known as a functional group, which we'll talk about later on in this chapter. The key takeaway from this problem that I'd like you to note is the formulas in organic chemistry provide you a hint in terms of how your atoms are connected to each other, which in turn simplifies the amount of guesswork that you have to do for a Lewis structure. So once we have our skeleton in place, we're going to form one bond each. So we've used up 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons. We have 6 electrons remaining. And where do we place our last 6 electrons? What atom is the most electronegative atom with an incomplete octet? Oxygen, that's right. So we place 6 electrons on oxygen. Now, are we done? Does this structure fulfill the octet rule? No. So we're going to take our lone pair on oxygen and form a double bond. This molecule is known as acetone, and it's a common organic solvent. So really focus on looking at the ordering of atoms in the structure, because most organic structures will be either condensed or provide a significant amount of information on the connectivity of atoms in that structure. So let's look at another example. I'd like you to work on and try to write out the Lewis structure for acetic acid. And I'd just like you to tell me, for this central carbon here, I'd like you to tell me the number of single and double bonds if you're responding in the chat. Otherwise, I'd prefer for students to use the annotate feature to help share their proposed responses. So we'll spend about 2 to 3 minutes on this example. Keep in mind the ordering of atoms in your chemical formula provides you a hint for the connectivity of atoms in your Lewis structure. And keeping with the theme of functional groups, this CO2H formula component represents another organic functional group known as a carboxylic acid. We'll talk more about that later. This molecule is known as acetic acid. It's the principal component of vinegar, actually. And it's actually what you're going to be titrating in the laboratory next week. So let's try to get a few responses in the chat or using the annotate tool. And we'll discuss this example in about 2 to 3 minutes. And the response I see using the annotate tool looks great. So allow me to clear this drawing, and let's now discuss this example. Part of what we're doing in this initial section in organic chemistry is starting to develop pattern recognition for common structural motifs when drawing Lewis structures. So for carbon, we have 4 electrons. We have 2 carbon atoms. For hydrogen, we have 1 electron per hydrogen, and we have 5 hydrogen atoms. For oxygen, we have 6 electrons, and we have 2 oxygen atoms. So that gives us
Professor,
Oh,
don't we have four?
yep, 4, yep.
I was just going to say.
Yep. Okay, so counting our total number, we have 12 plus 8 plus 4. That gives us 24 electrons. Okay, so now that we have our total electrons counted, looking at our structural motifs, we have our 2 carbons as our central atom. The leftmost carbon is surrounded by 3 hydrogens. The rightmost carbon is surrounded by 2 oxygens, and we place our last hydrogen on our remaining oxygen. So this CO2H moiety, or the carboxylic acid functional group, we'll see once we fill in this Lewis structure, and we'll highlight the carboxylic acid functional group. Now that we have our skeleton, we'll form 1 bond each. We've used up 2, 4, 6, 8, 10, 12, 14 electrons. We have 10 electrons remaining. We place our lone pairs on each of our oxygen atoms. In turn, we've used up all 10 electrons. As our central carbon doesn't have a complete octet, we're going to move a lone pair down and form a double bond. I'd like you to note that this moiety, this CO2H moiety, or CO2H functionality, is known as a carboxylic acid. So when you see this arrangement of atoms in your chemical formula, it's highly likely that you have a carboxylic acid functional group. By the same token, in our earlier structure of acetone, this CO functionality is known as a ketone, or more generally as a carbonyl. And the carbonyl functionality consists of a carbon double bonded to oxygen. This is our first real introduction to this idea of functional groups, and the real beauty of functional groups is they allow you to take shortcuts when writing the structures for complex organic molecules. Does this make sense so far? We'll talk more and we'll provide you a table for each of the functional groups. We're actually going to start talking about molecular geometry momentarily, actually. But before we get to that, we're going to look at a few common anions. And these are not just randomly chosen. These are actually common species that you'll see throughout your organic chemistry experience. So BH4 minus is a pretty interesting species. It resembles a lot of very common reducing agents used in organic chemistry. So boron has 3 electrons to its name. Hydrogen has 1 electron, and we have 4 hydrogens. But since we have an anionic species, what do? Do we add or subtract the charge?
Add.
Add the charge, exactly right. So we add 1 electron to our total. That gives us 8 electrons. We put boron as our central atom. We surround it with our hydrogen atoms, and we form 1 bond each. That gives us 0 electrons remaining. But as this structure is charged, we respect the fact that this structure is charged by placing the structure in brackets and indicating the charge as -1, because the charge is -1 in the upper right-hand corner. Now, the reason why I say a lot of these compounds containing a metal and hydrogen are very efficient reducing agents, these species in general are known as quote-unquote hydride sources. If we look at a boron-hydrogen bond, the hydrogen has a substantial amount of anionic character, otherwise known as hydride character. So these This structural motif often indicates a hydride donor. And we'll see this a lot when we look at mechanisms behind reducing agents. And the reason why we're able to talk about these species as hydride donors stems from the fact that this boron hydrogen bond is polarized towards hydrogen. So we see a direct link between the principles of electronegativity and the reactivity of our various chemical reagents. So the electronegativity isn't just taught as a tool to defectively draw Lewis structures. It can also help you identify reactivity patterns in chemical bonds. Okay, so with that said, I'd like you now to start working on the following two Lewis structures. So I'd like to see some annotated Lewis structures drawn in the following sections of our whiteboard. Or if you're unable to submit or perform annotations on your device using the Zoom Annotate tool, what I'd like for you to share for each of our structures is the number of lone pairs. For this first structure, I'd like you to tell me the number of lone pairs on nitrogen. For the second structure, I'd like you to tell me the number of bonds to oxygen. So we'll spend about 3 to 4 minutes on the following example. We'll draw some common Lewis structures for common anionic species that you'll see in this class, and then we'll discuss the Lewis structures for each of these examples. And if you have any questions or if you'd like to share your proposed responses, don't be shy to unmute and share your responses verbally, or to share your responses in the chat or on the whiteboard using the annotate feature. And the responses we see for this first Lewis structure look great. So let's discuss this first example. And as we already have students sharing the second example, I'll allow students time to share their proposed responses for the second example. It's wonderful seeing students participate in the chat and using the annotate feature, as it really helps give me a sense of how everyone is progressing through the course material. And if you have any questions at all, don't hesitate to ask. And the responses I see using the annotate tool are perfect. So allow me to clear these annotated responses and we'll draw out our instructor response just so that way all of our notes for this session are able to be read after we export this note set. So for carbon, we have 4 electrons and we have 2 carbon atoms. For nitrogen, we have 5 electrons. For hydrogen, we have 1 electron and we have 6 hydrogens. So that in turn gives us a total of 13, 19. We then add 1 because we have a -1 charge. That gives us 20 electrons total. Following our ordering, we place our carbon, nitrogen, and second carbon as our central atom. Each of our carbons are surrounded by 3 hydrogens. And that's it for our skeleton. So we'll now form 1 bond each. Okay, we've used up 2, 4, 6, 8, 10, 12, 14, 16 electrons. We have 4 electrons remaining. Now we place our remaining 4 electrons on our nitrogen atom, and that in turn completes our Lewis structure. To respect the fact that this is a charged molecule, we put the structure in brackets and we indicate the charge. These nitrogen-based anionic species are wonderful organic bases. So you'll see these nitrogen anion species used commonly for acid-base reactions in organic chemistry. This is a relative of probably the most commonly used organic base, which is lithium diisopropyl amide. You probably wouldn't want to actually make this amine if you're trying to run an acid-base reaction, as the starting material for this amine smells terrible. But nonetheless, these kinds of structural motifs show up a lot in organic chemistry, especially in the chapter on acid-base chemistry. Let's look at this next structure. This is a derivative of methanol known as methoxide. So carbon has 4 electrons to its name. Hydrogen has 1 electron and we have 3 hydrogens. Oxygen has 6 electrons and we add 1 electron because we have an anionic species. That in turn gives us 14 electrons to work with. We place our carbon surrounded by our 3 hydrogens and 1 oxygen. And then we form 1 bond each. We've used up 8 electrons. We have 6 electrons remaining, and we place our remaining 6 electrons on oxygen. Methoxide and other alkoxide species are wonderful reagents for, again, acid-base reactions and for elimination and substitution reactions. So you'll see these structures a lot more later on in this course. Any questions on these 2 examples for drawing Lewis structures of anionic species? If not, let's continue on and let's look at cationic species. So we're going to look at a few common cationic species that we see in organic chemistry mechanisms. The first of which is a protonated amine. So these are very common structures that we often see as the result of acid-base reactions in organic chemistry. So counting our valence electrons, for carbon, we have 4 electrons and we have 2 carbon atoms. For nitrogen, we have 5 electrons. For hydrogen, we have 1 electron and we have 8 hydrogen atoms. However, because our species is positively charged, we need to subtract 1 electron from our total. So we have, instead of 21 electrons, just 20 electrons to work with. Now again, looking at our formula, the formula provides us structural information on the connectivity of our atoms. So I'm going to put my carbon, and my nitrogen as my central atoms. I'm going to surround carbon with 3 hydrogens for that CH3 formula feature. I'm going to surround my second carbon with 2 hydrogens, and my final nitrogen gets surrounded with 3 hydrogens. I'm then going to form 1 bond each. I've used up 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 electrons. And now I'm going to place my structure in brackets and indicate the charge. These protonated nitrogens, or these nitrogen species with a positive charge, are typically known as what are known as ammonium salts. And they're actually quite useful, not just for acid-base reactions, but also for phase transfer reactions, which are really quite interesting when you think about how they work. Okay, so we've seen a representative example. Now let's take a look, and I'd like you to draw the Lewis structure for the following 2 molecules. For the first structure, I'd like you to tell me the number of lone pairs on oxygen. And for the second structure, I'd like you to tell me the number of bonds to oxygen. So we'll give everyone, again, another 3 to 4 minutes to work through the following Lewis structures, and then we'll discuss. Again, don't be shy to share your proposed responses in the chat or using the annotate feature. And if you have any questions at all, don't be shy to message in the chat or unmute and ask your questions verbally. I always like the problems that I assign to have a dual purpose, and a lot of these structures you will see again as part of organic mechanisms. And the responses that I'm seeing in the chat look quite reasonable so far. And the response I see for the first Lewis structure of hydronium looks perfectly reasonable, and it also matches many of the responses that we see in the chat. I'd like everyone to take a few more minutes and work on the second Lewis structure. This is quite interesting. This is a common intermediate observed in both Friedel-Crafts acylation reactions as well as other reactions involving carboxylic acids and acyl chloride functional groups. So we'll discuss the second example. I'd just like to see a student response either in the chat or using the annotate feature. And the responses I see in the chat also look reasonable. Everyone has caught on to probably the most interesting feature of this functional motif. Exactly right. We have this very unusual carbon-oxygen triple bond. Perfect, perfect. The responses I see in the chat look great, so I'm going to clear annotation, and then I'm going to provide the instructor annotation, just so that way everything can be exported into Canvas once we finish this note set. So for hydrogen, we have 1 electron, and we have 3 hydrogens to work with. For oxygen, we have 6 electrons. We subtract 1 electron from our total because we have a positive charge. That in turn gives us 8 electrons to work with. We put oxygen in the center, surround it with 3 hydrogens. We form 1 bond each. That gives us 2 electrons. And then finally, we place our lone pair on oxygen, and we place our entire structure in brackets with a positive charge to denote that this species is a cationic species. This is known as hydronium. It's commonly produced as a byproduct from many acid-catalyzed elimination reactions. Let's look at this next species. So first and foremost, carbon contributes 4 electrons, and we have 2 carbons. Hydrogen contributes 3 electrons. Oxygen contributes 6 electrons. And then we subtract 1 electron from our total. So we have 14, 15, 16, 17 minus 1 gives us 16 electrons to work with. We place our 2 carbons as our central atoms, and we surround our rightmost carbon with an oxygen atom and our leftmost carbon atom with 3 hydrogens. Then we form 1 bond each. We've used up 2, 4, 6, 8, 10 electrons. We have 6 electrons remaining. And then what we're going to do is we're going to place our remaining 6 electrons on oxygen. As we do not have a complete octet, we're going to move a lone pair down to form a double bond. We're still not done, so we're going to take another lone pair and form a triple bond. Next, we'll note that this entire species is a cationic species by placing the structure in brackets and assigning a positive charge. Does this make sense to everyone so far?
Yep.
Perfect. Okay, so we've talked a lot about charged molecules. Let's talk more about how do we assign formal charges? How do we identify the charge of each of our atoms in a Lewis structure? So in general, favorable Lewis structures have atoms with small formal charge values, have few atoms with non-zero formal charges. They place negative formal charges on electronegative atoms and positive formal charges on less electronegative atoms. The formal charge on an atom can be defined as the group number minus the number of bonds plus the number of lone pair electrons. So notice the distinction. Bonds, lines drawn. Lone pair electrons, number of dots, discrete number of lone pair electrons. Now, what's really interesting is that the total charge of a molecule is equal to the total formal charge of all atoms in the molecule. Now, I always like to throw in some examples that are relevant to biology, since many students taking this class are biology majors, and many of them say, well, what's the point of learning all of this organic chemistry? Well, it provides you a lot of insight into the behavior of biological systems and mechanisms behind many biological processes. When you eventually transfer, I would highly recommend taking a bioorganic graduate course after you finish your organic and biochemistry sequence, as it really ties everything together wonderfully. Now, why am I bringing up biology here? Would anyone like to tell me from this formula what structure am I talking about? What fundamental biological structure am I talking about from this formula? Any biology majors in the chat would like to share their guess? Let's draw it out. Let's draw it out. So counting electrons. So counting electrons, just to do our electron count. For nitrogen, we have 5 electrons. For hydrogen, we have 5 electrons. For carbon, we have 4 electrons, and we have 2 carbons. For oxygen, we have 6 electrons, and we have 2 oxygens. Notice this structure overall is neutral, but it does have atoms that have a formal charge. So adding up our total, we have 10 plus 8 plus 12. So that gives us 30 electrons to work with. So I'm going to follow my structural formula. We actually see a functional group at play here. We have a carboxylic acid, and we also have an amine functional group. 2 functional groups that we've seen before. I see students typing in the chat, amino acid, glycine. Yes, this is the fundamental structural motif of an amino acid. Yeah. Okay, so let's draw out this structure. So we're going to place our skeleton of nitrogen, carbon, carbon, and oxygen. We're going to surround our nitrogen with 3 hydrogens, surround our carbon with 2 hydrogens, and surround our rightmost carbon with an oxygen. We're then going to form 1 bond each. And that's used up 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons. We have 12 electrons remaining. Now what we're going to do is we're going to place our lone pairs on oxygen. We've used up all of our electrons, and to fulfill the octet of carbon, we're going to take one of our lone pairs on oxygen and move our lone pair down to form a double bond. For formal charges, there are charged atoms in the following structure. Let's first look at nitrogen, and let's calculate the formal charge of nitrogen. So, nitrogen has a group number of 5, and how many atoms are bonded to nitrogen? 4. That in turn gives us a formal charge of +1. So we'd in turn note the nitrogen's formal charge with a positive symbol. Okay, let's look at this middle carbon. So this carbon in the middle. Okay, carbon has a group number of 4. It has 4 bonds, so it has a formal charge of 0. You do not need to write a formal charge of 0. That would create way too much clutter in your structure. Okay, let's look at the topmost oxygen. Let's look at the topmost oxygen. We have a group number of 6. How many lone pair electrons do we have? How many lone pair electrons do we have? Not lone pairs, but lone pair electrons. Not lone pairs, but lone pair electrons. How many dots? We see on this top oxygen. For formal charges, you look at each atom individually, but yes, the logic behind your count was correct, actually. We have 4 lone pair electrons, 4 dots on this top oxygen. And how many bonds do we have to this top oxygen? How many bonds do we have? 2. So that gives us a formal charge of 0. Let's look at the bottom oxygen, this oxygen right here. We have a group number of 6. How many lone pairs do we have on the bottom oxygen? How many lone pair electrons do we have on the bottom oxygen? We have 6 dots and we have 1 bond. That gives us a formal charge of -1. So we note our oxygen's formal charge again with a minus symbol. Now, one thing I'd like you to note, this structure overall is neutral, because if we add up our formal charges, we get a formal charge total equal to 0, which matches the fact that this molecule is not charged overall. It just has charged atoms. Does that make sense to everyone? These molecules that contain both a positive and negative charge are known as a Zwitter ion. And you'll see a few other species with this kind of characteristic where you have both a positive and negative charge in the same molecule. We'll talk a lot more about these amino acid functionalities in the chapter on acid-base chemistry. So I'd like you to now look at ozone, O3. And although this looks like a very simple formula, it houses a lot of complexity in terms of formal charges. So I'd like everyone to try to draw a Lewis structure for ozone, and then I'd like you to assign formal charges on each of our oxygen atoms. And that's already a hint that the formal charges may be different. So let's spend about 2 to 3 minutes on this problem, and then we'll discuss momentarily. And don't be shy to share your responses in the chat or using the annotate feature. And I would double check the octet rule and the electron count as well. I would make sure your structure has the correct total number of electrons and that you form a double and triple bond only when completely necessary. Let's try to get a few more responses, or if anyone would like to revise their annotated structure. The majority of the structure looks quite good, but we just need to adjust and account for the electron count and the total number of electrons in this structure. Let's try to get a few more responses, and we'll discuss in about another minute to a minute and a half. And the response that I see in purple using the annotate feature looks great. Let's try to assign some formal charges, and then we'll discuss in about another minute to a minute and a half. And If anyone wants to jump in and provide any input on the drawn Lewis structures and assign formal charges on any of these 3 oxygen atoms, I'd greatly appreciate that in our class discussion. And don't be shy, even if you haven't drawn this exact Lewis structure, if you'd like to chip in and draw out an assigned formal charge on any of these oxygen atoms, it would be wonderfully instructive to and helpful for our overall class discussion. Otherwise, we'll discuss in about another 30 seconds to a minute. So we have a reasonable Lewis structure. What do the formal charges look like? And the assigned formal charges, both in the chat and via the annotate feature, look great. So let's clear this drawing and allow me to draw out the instructor annotation, just so that way when I export it to Canvas, everything is visible. So for oxygen, we have 6 electrons times 3. That gives us 18 electrons. Doesn't matter what the central atom is. All we have is oxygen. We're going to form 1 bond each. That gives us 14 electrons. Then we're going to place our lone pairs on the outermost oxygen atoms first, followed by our inner oxygen atom. Now that we're out of electrons, to fulfill the octet rule, we get rid of our lone pair and we form 1 bond. Now, to calculate formal charges, to calculate the formal charge of our leftmost oxygen, we see our group number is 6. We have 6 lone pair electrons and 1 bond. That gives us a formal charge of -1. Looking at the formal charge of our middle oxygen atom, we have a group number of 6, we have 2 bonding electrons, and we have 3 bonds. That gives us a formal charge of +1. Finally, the formal charge of our rightmost oxygen, we have a group number of 6, we have 4 lone pair electrons and 2 bonds. That gives us an overall formal charge of 0. As we see, if we add up our formal charges, the total formal charge, the total charge of our molecule is 0. Ozone's quite interesting, and we'll actually see ozone used in chemical reactions in this class. It primarily reacts with double bonds to generate ketones and carboxylic acids via ozonolysis. So, this is a good stopping point for today. We'll continue on with our review next class session, where we'll begin to introduce shortcuts for predicting formal charges, shortcuts for drawing Lewis structures, condensed chemical formulas, and we'll start to delve into molecular orbital theory to begin to describe bonding and to begin to start to understand bond length, strength, and reactivity. So I'll stop the recording for today.